You may begin, please.
Well, hello everyone. Thank you for joining us for the webinar today. Today's webinar is going to be a continuation of last week's discussion where we talked through some of the hydropower capabilities of the Corps of Engineers. Today we're going to dive into a deeper technical review of micro-hydro technologies. And so I've got Charlie Allen, who's a senior mechanical engineer at the Hydroelectric Design Center, and myself, Jeanette Fiess, are here to talk through some of those technical discussions with you. Charlie's going to lead through all of that, and we'll be able to walk you through a variety of different technologies. So we're looking forward to the discussion with that. I'm going to briefly just give a quick introduction of the Regional Energy, Sustainability, and Lifecycle Cost Analysis Centers of Expertise. You may have seen, you'll see on the far left of your screen there, the Sustainability and Energy website that we have linked. It's also on the slide here. These regional sustainability centers were stood up several months ago, and these centers, what we've done is we are working to broaden technical capabilities across the Corps of Engineers and raise understanding and awareness of a variety of different technical competency areas. And so what we've done is we've assigned different responsibilities to the different regions. So if you are looking for, on the left, you can see on the slide there, it's a small picture, I know, but you can see that we've assigned responsibilities for a variety of different technology areas. If you're looking for support in lighting or building envelopes, waste, hydropower, like we're going to be talking about today, each of those different areas is highlighted on the left side of the page. You can click on that, and that will take you to the technology page where you can find additional information about who our experts are across the Corps of Engineers in these different areas, and what region has responsibility for putting you in touch with experts if you aren't able to get the answers that you need from the website. So I raise that just to bring your awareness to these recently assigned regional centers of expertise. We are working to get our websites up and going and get our programs in place to be able to provide support across the Corps. So one of the assignments that Northwestern Division has been given is that for hydropower. We have that assignment because the Hydroelectric Design Center is located within our region in NWD. And so I want to give Charlie a chance to walk us through what HDC is in a brief 2-minute recap of what we talked about last week. And then Charlie's going to dive into the details of micro-hydro. So with that introduction, Charlie, I will turn it over to you, and you can walk us through all the details of what we're going to be talking about today.
Thank you, Jeanette. As Jeanette has said, this is a follow-on to the webinar that was presented a week ago, and we're going to be going into more depth and details of what small hydro is and how it might be applicable for your uses. First, however, I'd like to do a very brief review of what the Hydroelectric Design Center is, who we are, and what we do. The Hydroelectric Design Center is the Corps of Engineers' mandatory center of expertise for hydropower and large pumping plants. We're located in Portland, Oregon as an adjunct, shall we say, to the Portland District. We have about 75 engineers and technicians in the HDC staff. These are mostly electrical and mechanical engineers. Think of us as the machinery people, if you will, and that machinery is within the context of hydroelectric powerhouse machinery. There are also about 6 economists on the staff of HDC as part of our Hydro Analysis Center, and these folks do economic studies for water use and water allocation. And as a subset of that, they do economic studies for hydropower. From my perspective, the best way to think about HDC, or the best way to think of us, is as a captive in-house consultant. We are, without question, an integral part of any hydropower products delivery team, but there are lots of PDT roles and functions that need to be filled by a district and district personnel rather than being filled by HDC. And the slide that you have in front of you goes into the major divisions of those responsibilities for a hydropower PDT. Now, moving into the primary subject matter for this presentation, the goals are to present different types of equipment, explore the conditions under which that equipment can be used. We're going to provide some sample costs, talk about risks, and explore some time frames for developing a small hydropower facility. And we'll also provide some screening information for quick assessments by those folks that are in the field, looking at whether or not a site really has potential or it's just a trickle flowing down the side of the hill that isn't going to amount to much. Why hydro? In this day of sustainability and renewable resources, hydro tends to speak for itself. There are no greenhouse gases with hydropower generation. It is sustainable, you get free fuel, and of the three primary renewable energy producers, that is hydro, wind, and photovoltaic, hydro has the highest capacity factor, which means for a given installation size or how many megawatts of generation capability you install, you're going to get more energy from a hydro facility than from any of the other primary renewable sources. Having talked about the advantages, we also have to acknowledge the disadvantages, the main ones being environmental impacts, especially when you talk about impounding a free-flowing stream. But there's also a large upfront investment that speaks to the financial hurdles that need to be conquered. Project management, engineering, regulatory permitting, and of course construction are all elements of a major hydropower development that have to be funded before you get one bit of payback. And the payback for a typical hydro facility is long, on the order of 20 to 50 years, depending on many variables. When one talks about the size of hydropower developments or the scale of hydropower, there's really no universally accepted definition for what big, small, mini, and micro are. But the numbers you see on your screen right now I won't get much dispute from my fellows in the hydropower community for these numbers, with small hydropower being anything less than 10 megawatts, mini being less than 1 megawatt or 1,000 kilowatts, micro being smaller than 100 kilowatts, and pico being less than 10 kilowatts. And to put this in perspective, your average house requires about 5 kilowatts of capacity. So even pico hydro at 10 kilowatts is probably enough to power 2 houses. And again, putting it in a different scale, large powerhouses in the United States, Grand Coulee has an installed capacity in excess of 6,000 megawatts. Bonneville Dam at the end of the Columbia River has an installed capacity of about 1,000 megawatts. Typical powerhouse sizes or installed capacity that you will see in hydropower facilities in the south and southeast are on the order of 40 megawatts to, shall we say, 200 megawatts. There will, of course, be some bigger, but that's average in that region of the country. For our purposes today, there are really 2 basic categories of hydropower that we'll talk about. Those that get the water from a closed conduit and those that get it from an open channel. And the first we're going to talk about is closed conduit, otherwise known as a pressurized pipe. Locations where you might find this and where it would be applicable would be a dam with a discharge pipe, or perhaps from a pressure reducing valve. A pressure reducing valve, or a PRV, is most typically associated with municipal water distribution systems. They come into play for circumstances where your reservoir is at a very high elevation, shall we say, on the top of a hill. And as the water flows down the hill in a pipe, the pressure at the bottom where your water distribution system is, or where your treatment facility is, just gets too high. And so this PRV, or pressure reducing valve, pulls some of the pressure out of the water. It's basically wasted energy, And you could perhaps, instead of using the PRV to burn off the energy, put a turbine in there and actually generate some power from it. Other closed conduit or pipe applications would be any place you've got a waterfall or an outfall from a water treatment facility. Once again, basically any place there's a change in elevation of your water, you've got at least a potential for considering a site. Now we're going to go into about 5 or 6 slides with various machines and machine types for these pressurized conduit applications. This first slide is relatively new, pre-packaged technology provided by Toshiba Corporation. These units come any place from 5 kilowatts to 250 kilowatts in size. They come pre-mounted on a skid. You basically cut a section of pipe out of your line, you pour a concrete pad to mount this thing on, you put it in and hook up the electrical connections, and you're generating equipment. It's not quite that simple because you still need some kind of a weatherproof enclosure for the controls mechanisms. That is those little computers that help run the whole thing. But that's just a weather-tight box, if you will. This second unit is what's called the Terminator by Clean Power. They're a, I think, Norwegian entity. They certainly come out of Scandinavia. Again, this is a prepackaged unit with the turbine runner and the generator all in one box. Bolt it up where you can and get power out of an existing large pipe. The right-hand picture, of course, that shows a picture of a gentleman in the yellow suit, gives a scale. This is a conventional turbine. In fact, this picture is of a 50-year-old turbine at a valve house in Afghanistan. The white device in the middle that's kind of got the decreasing spiral is the turbine. The brown round device to the right of that, going into the rear of the picture, is the generator. And off to the left of the turbine, you'll see a little box that's about 18 inches by 12 inches. That's the governor and the hydraulic pumping unit, supplying hydraulic power for the hydraulic controls of the machine. This one's 75 kilowatts at about 250 feet ahead. And this is truly a real turbine, just shrunk small. This next slide is of Lucid Energy's in-pipe turbine. This is a very new technology with a new application. These are classically used to replace a pressure reducing valve. You get a section of pipe where you need to drop the energy or the pressure, install some of these in. I think the energy generated by each of these turbines is something on the order of 5 to 25 kilowatts, but you can cascade them relatively close to each other. Again, an emerging technology that's just starting to come online. I don't know how many of these are installed in the United States. Last of all, a larger powerhouse with a conventional impulse turbine, and you're not going to manage to see the impulse turbine because it's encased in that sheet metal type housing in the right-hand picture. But the main point of this slide is not the turbines. It's the fact that when you get into energy production of this size, in the order of 1 megawatt and larger, you need a lot of powerhouse systems to help run and operate your equipment. On the left-hand slide, sorry about that, on the left-hand side in the foreground you see a hydraulic pumping unit complete with reservoir and high-pressure lead and lag pumps. On the very back wall of that left-hand picture, you see a lot of conduit, switchgear, and electrical switching devices. Then in the right-hand picture, on the rear and the right hand, you see 2 electrical control cabinets that are in the order of 8 feet tall, 3 feet wide, 4 feet deep. These house all of the protection and controls and switchgear that's needed to support this size of an installation. Point is, when you get into a megawatt or larger, it starts getting big in terms of the infrastructure needed to support the generation. Now, switching from closed conduit applications to open channel installations. Open channel would be things like irrigation canals or perhaps free-flowing rivers or streams. Could be a tidal area. This is very much an emerging technology that there's been a whole lot more on the shall we say, wishing and dreaming side than there has been in the actual development and deployment side. Being an emerging technology, there are the associated higher risks, and there's really less clarity of how to develop or how would we proceed with putting in one of these installations. But there are approximately 25,000 miles of irrigation canals in the western United States. And in my opinion, a canal installation for this type of technology really holds a lot of promise. Each of the units is only 5 to 10 kilowatts, but the neat thing is you can cascade these units as you go down the canal and put in one every 100 feet or one every 300 feet or so, depending on your canal geometries. You need a water velocity in the canal of about 6 feet per second, and the canal can't be small. Something on the order of 15 feet wide by 8 feet deep, with a flow rate on the order of 200,000 gallons per minute. But here you see the first prototype installation of a hydrokinetic turbine in a canal in the United States. This was installed initially about 18 months ago, I believe. The picture on the left shows the turbine being installed. The yellow box mounted on the left-hand side of that turbine is the generator and the controls equipment. The only thing, this comes to the canal prepackaged. The only thing you have to do is put two mounting posts, two anchoring posts on each side of the canal, and string a cable to each end of this turbine to hold it in place. String the umbilical electrical wire to your load point or your connection point, and you're ready to go. The right-hand picture shows that turbine operating in the filled canal. Okay, we've talked a little bit about some of the equipment, some of the machinery. Now let's talk about project considerations and things that need to be thought about as you consider moving forward with a hydro development project. And I'm going to provide about 6 or 7 slides here. Each slide is a different consideration, and this part of the presentation is kind of disjointed, so please stay with me as we hit one point, then another point, then another point in no particular order. So first to talk about is generation and load. You can have a number of combinations here. First one being isolated generation supplying an isolated load. That is, you've got a remote site someplace and you just want this generator to supply power to this building or this facility, and they aren't going to be connected to a grid or a distribution at all. They're an island by themselves. Second option, of course, is to get hydropower generation that's connected directly to a distribution grid. That's pretty simple and straightforward. And another option is connecting the hydropower generating equipment to the grid, but then having capability to have that hydropower generator serve as a backup generator to power essential facilities should the grid go down. In all of these cases, the costs are very dependent on the details. And among those details are the amount of power that's being generated, the transmission distance, and depending on the loads and the type of equipment you have, the maximum distance could be 2 miles. That's for, shall we say, less expensive equipment, or it could be as much as 25 miles, but the cost of the equipment needed to support a 25-mile transmission is, of course, more expensive. It depends on the type of load that's being served, and of course depends on the requirements that you have for a generation response in case of a grid failure. Equipment costs. Again, it's very site dependent and there's a huge variation. And this slide is fraught with pitfalls when it gets used against me, folks. But to give you just a sense of the ballpark, for a 5 kilowatt installation on a closed conduit could be any place from from $10,000 to $100,000. Obviously, that $10,000 price tag is for a facility that literally installs itself. It's very simple and very straightforward with, again, very simple equipment. For 50 kilowatts, $50,000 to $500,000. And if we're talking 1,000 kilowatts or 1 megawatt, then we're up at $500,000 and on up for that size of an installation. For open channel, right now those 5 to 10 kilowatt units that you saw 2 or 3 slides previously are priced out at $40,000. I certainly expect that as these things come online, we get some production economies of scale. That price per unit will drop substantially. But for a 1 megawatt installation or 1,000 kilowatts, I did some estimates a while ago, and that installation was on the order of $6 million to get 1 megawatt of generation up and going. Operating and maintenance costs. First of all, any of this equipment can be automated and automatically monitored, and you can automatically monitor it at any point. Primary would be perhaps the maintenance shed at your facility. For developed technologies, routine maintenance should be less than 8 hours per week, probably much less than that, and you should have a major maintenance outage only once per year. That maintenance outage should last about 1 week, and it should take any place from 80 to 160 man hours to do the required annual maintenance. For the emerging technologies, there are really too many variables to go into to comment on what the operations and maintenance tail would be on those. And if you have one of those that you want to put on the table, we're going to have to deal with it on a case-by-case basis. Implementation schedules. I'm starting to sound like a stuck record here. Highly variable depending on the site. They can be as short as 6 months, but again, that's for a very small unit, something on the order of 5 kilowatts, maybe to a max of 20 kilowatts, where the generating unit is sitting on a shelf waiting to be grabbed and installed. More likely, implementation schedules are on the order of 1 to 3 years. And if you need NEPA permitting or EPA permitting, you're going to need to add yet more time. In general, this equipment is pre-engineered or custom made. Very little of it is, and only the small stuff is off the shelf. Pre-engineered meaning it's made to order, the plans, the design is ready to go, but people aren't going to start manufacturing these pieces until they receive an order for them. Now let's go to what I call the benefit equation, which really goes to the crux of the decision process for whether or not someone is going to proceed with development of a site. The total benefits that a hydropower facility generates over its lifetime is equal to the energy generated over its lifetime minus the one-time construction costs, minus the O&M costs over its lifetime, plus the ancillary benefits. We on the engineering side of the house are really pretty good at providing values for the energy generated and the construction costs and the O&M costs. But we need the engineers and the hard numbers folks need to partner very vigorously with the customer, attempting to either qualitatively or quantitatively identify the ancillary benefits, which can be something like meeting national and Army policy objectives for energy security or energy use reduction, or greenhouse gas emission reductions, or meeting the net zero goals that we've got targeted for us in the next 5 to 7 years. The hard numbers side, that is the pure engineering side, recognizes and acknowledges that these policy objectives may well be the final driver or the primary driver in whether or not the facility gets built. They may be the trump card. And so we need to put the hard numbers together with the softer policy issues to decide whether a facility is a go or a no-go. When we talk about existing non-powered dams, that is the flood control dams for the Corps of Engineers, or the navigation dams on our major river systems like the Ohio, the Mississippi, the Missouri, the Arkansas, and others, or perhaps even an irrigation reservoir that do not have existing hydropower facilities installed in conjunction with these dams. The potential at these non-powered dams has been investigated and evaluated many times. The Department of Energy and the National Hydropower Association both maintain indexes and databases of these dams. Everybody who's in hydropower knows what's out there and knows its potential. That's both private developers and utilities. And indeed, you know, there was a renewables push in the 1970s and again from 2005 to the current date, where there were energy tax credits for developing renewable and sustainable energy. So these sites have been looked at before. We can be fairly confident of that. And if there's no power at them, it's because there wasn't and isn't an economically or environmentally viable, or it's because those sites were not and are not economically or environmentally viable using conventional evaluation criteria. And I stress the conventional evaluation criteria that demands a profit from the installation of these sites. That said, the whole point of this is that when you walk out and you look at the dam and there's no power at it, it's not because folks don't know about it. It's because it hasn't yet crossed the barrier to being viable by conventional means. So our ancillary benefits that I talked about in the previous slide need to be large enough to take these sites from what has previously been not economical into the state of being viable. And I would again stress that what I just talked about is for sites that are, shall we say, in the public domain or that are readily available. Sites on Army installation property have probably been far less scrutinized because the developers and the utilities didn't want to have to deal with the Army security issues that they know would happen when they came on base. So sites on installation property deserve, shall we say, a harder look or a fresher look than perhaps sites that are off of installation property. Now let's go to what I call a power equation. Hydroelectric power, the amount of power generated, is simply equal to the head at the site times the flow at the site times a proportionality constant. And for our purposes, I've rolled the equipment efficiency into that proportionality constant. Head is the amount of the elevation and the difference of the water. Think of it perhaps as the height of the dam or the distance that a waterfall drops from the top of the water to the bottom of the water. Flow, measured in cubic feet per second, gallons per minute, doesn't matter. All it does is change the proportionality constant. Obviously, accurate values of head and flow are critical to determining what your power potential is at the site. And as you look at sites, be aware that flow and head will probably vary seasonally. As a practical example, just to give you a sense of what we're talking about here, at a 20-foot head site, which is roughly 8 pounds per square inch of pressure, you need 74 cubic feet per second or 33,000 gallons per minute being delivered through a 4-foot diameter pipe or penstock in order to generate 100 kilowatts. If you increase that head to 100 feet or approximately 43 pounds per square inch, then you only need 6,700 gallons per minute delivered in a 20-inch diameter penstock in order to generate that same 100 kilowatts. And the size of the penstock here is a little bit important because the physical size of the equipment, the dimensions, if you will, of the turbine and generator are generally proportional to the size of the penstock that's feeding it. So physically smaller equipment means physically cheaper to build. The bottom line here is the more head you have, the higher the pressure you have, the cheaper it is to install the equipment and the easier it is to get payback for your investment. Now, moving on to some screening formulas that you can use to go out and look at that site that you have to see if it, shall we say, cuts first muster. The formulas will be on the next slide. We have to slog through the upfront information first. I've assumed an 80% efficiency on the equipment. Equipment efficiency actually varies from about 60% to 90%. 80% is a good middle of the range. The formulas on the next slide will get you in the plus or minus 25% range. And if at plus minus 25 you think it's still viable, it's time to start calling other people. H is equal to the head. It's the elevation drop of the water in feet, as I talked about previously. CFS is cubic feet per second of water flow. GPM is gallons per minute of water flow. And PSI is pounds per square inch of pressure. KW equals kilowatts of output. And you take whichever form you want to put it in of those input variables, use the appropriate proportionality constant, and come up with kilowatts. A note here, pipe velocity should be on the order of 7.5 feet per second. We can tolerate them faster, but if you get up in the order of 15 feet per second, you end up burning up more energy and friction in your pipe than the installation is worth. So you need to keep the velocities relatively low in the pipe. For a major installation, 7.5 feet is what we work to. Just a brief talk about some of the impediments to hydropower. First of all, legal authorities, especially on any federal dam. Congress dictated what that dam could be, the purposes for which that dam could be used. Among them are local water usage and water rights, flood control, power generation, recreation, and navigation. But the point is that existing dam may not have an authorized purpose of hydropower generation, and we may need to go back to Congress to get them to tweak their authorizations a bit. And of course, there's a host of permits. Environmental Protection Agency, National Environmental Policy Act, Endangered Species Act, and these are only 3 of the big ones. There's probably another half dozen that could be added to this list. And of course, whenever you put in the facility, pay attention to the costs of O&M. They may be minimal, they may be substantial. Again, it's dependent on the eaches. So now that we've talked about the equipment, talked about where it can be applied, gone over some of the situations where you would or wouldn't put it in, and some of the project considerations, let's summarize that, if you will, in what the attributes of a good site might be. High head, obviously. The higher the head, the cheaper it is for installed kilowatt. Minimal disruption or intrusion on a free-flowing stream or river. An existing dam is a great possibility for a site because whatever the environmental impacts are, they've already been done, they already exist. Close to the grid connection or the load point helps a lot because then you don't have the cost of transmission involved, both the cost of installing the transmission line and also the energy losses as you put electricity through that transmission line. Constant flows mean that you will get a more generation per installed dollar, and any irrigation canal with sufficient flow, if you're willing to tolerate an emerging technology scenario, is a great place. Now on the flip side of the coin, let's talk about the attributes of a difficult site or things that are going to make it rough for us. Impounding a free-flowing stream. In other words, building a new dam. Almost a functional non-starter. Diverting a substantial amount of flow from a stream will also make life difficult for getting the site permitted. A large distance to the grid connection point or to the load makes things difficult, though not impossible. And any place you have endangered species or migratory fish in the water, it's going to be a problem. Excuse me. Finally, this is the where do we go from here slide, or how to proceed. The first thing would be for the installation or the Army facility to identify and do a preliminary screening at the site. Use those screening equations, go out and estimate your head and your flow rates, and see if it pencils out to the amount of power that you need or you think is worth developing. If the site passes that initial screening hurdle, then probably the next step would be contacting the Army Corps of Engineers geographic district that serves the installation for scoping discussions. If that geographic district isn't familiar with hydropower, or if you don't know who to go to at the district, alternate contacts are either Jeanette Fiess or some of us at HDC. We'll have that contact information in a later slide. And we can facilitate the discussion with the geographic district. Once the geographic district gets involved, there's some more scoping discussions and probably a more detailed screening level to determine the next step. And then if the site continues to show merit, it's time to move forward with the project process. Establish that a multidisciplinary team led by the district project manager. That multidisciplinary team includes folks from HDC for the machinery part of it, but it's contracting, legal, permitting, regulatory folks. Everything that goes into a multidisciplinary team needs to go into this one. Funding, of course, is always an issue, especially in the study phases. District PM and the district and or the installation need to come up with a way of funding it. I'll put in a plug here that says the Hydroelectric Design Center is a fee-for-service organization. Unfortunately, our services don't come for free. We're more than happy to provide an hour or two of conversation and initial discussion, but once it moves certainly beyond 8 hours of effort, we're going to need funding for our services also. I would like to point out that in this whole project process, as with any major infrastructure issue, there are multiple points in this process that can be a go or no-go decision. We peel the onion, and as we process through each layer or decision point, we ask ourselves, does this continue to look like it's going to be a viable project, or are we just hitting too many hurdles and roadblocks? And we can take the off-ramp at any time and stop expending funds if it appears that it's a no-go project. So in summary, we can use either closed conduit or open channel installations. There are a variety of turbine types. Costs and schedules unfortunately vary greatly, and we need to get into the specifics of each before we can comment on either of those. Use the screening equations to eliminate the obvious non-starters, and a reminder again that environmental issues can be huge impediments to the development of any site. So with that, there are the contacts: Jeanette Fiess, John Etzel, who is the Deputy Director of HDC.
From Matt Gibbs, he asks, would micro-hydro replace pressure-reducing valves on a domestic water supply system qualify as a renewable energy source?
Jeanette, I think you have to answer that one. I think it would, but I'm not in a position to provide an authoritative answer.
Fair enough, Charlie. Yeah. So the question, if if we put a micro-hydro in place of pressure reducing valve on a domestic water supply, yes, that's, I mean, to me, I agree, Charlie, that is new hydro capacity. There's no description or discussion in the definitions of the renewables that it has to be a specific application. So there are, hydro is considered a renewable technology when it is new since 1999. So there are rules about when it has to have been installed, but I agree that that does sound like something that would be considered renewable.
Excuse me for a moment if I can break in here. When you're looking at pressure reducing valves, remember that the only energy available is the inlet, the pressure at the inlet to the valve minus the pressure at the outlet to the valve. Don't make the mistake of assuming you can take all of the pressure in the conduit to generate power. You can only take the amount of pressure that the PRV itself burns off as you make these calculations for the available amount of power. I'm out.
Okay, now our guest, Mr. Robert Edwards, has a question regarding stream flow. He explains that stream flow varies. If we have access to stream gauge data, what would you recommend for a design flow for equipment sizing? For example, the mean flow, Q at 75% exceedance, etc.
This is Charlie. That's an excellent question. The classical large hydro answer to that question is approximately a 70% exceedance value. In other words, you will be spilling water, or you will be spilling about 30% of your water. In other words, the turbines aren't big enough to handle that. For a micro or for a smaller hydro installation, I think we'd really want to look at it again on an individual basis. I would certainly not size it any smaller than 50%.
The question was open channel. Open channel.
I'm sorry, this question was for open channel. I think the question perhaps is different. You need at least 6 feet per second in order to make these generators work. So this is more of a velocity question than it is a volume question. And I think the question should better be characterized, if you've got 6 feet per second of velocity in your channel, less than 6 feet, it's going to be very low generation or perhaps not work at all. And that's the way you need to come at this. And then we ask ourselves the question, how much of the year do we have a 6 feet per second velocity? How much of the year don't we have 6 feet per second velocity? And we factor that into the cost-benefit ratio for the facility. I hope that addressed the question. If not, please rephrase.
Okay, Robert, please let us know if that answered your question. If not, we'll move on. Okay, great. That seems to be all the questions we have today. Are there any more? Feel free to raise your hand or to type it in the Q&A box to the left. Okay, well that seems to wrap up the webinar today. Once again, thank you to everyone for joining us and Jeanette and Charlie for presenting. And just a reminder that this webinar was recorded and will be posted to the SME website. And please stay in tune for a possible time change for our weekly webinars. Lindsay Pruitt will be sending out a webinar reminder, so make sure you confirm the times before signing in with us. Thank you, and you all have a great day. Bye.